Welcome, my dear students. In the last class, we discussed about the internal direct product. I solved some examples. The last example we have to discuss is the Kalin-4 groups, and we have to prove a theorem that the internal direct product is equivalent conditions are there. We take a H1 and H2 are the two normal subgroups, and also intersection is equal to identity, and Hg can be represented as a H1 and H2 form. And if we have to these two equivalent conditions, this is the normal definition of internal direct products. And now if we show that I say that the equivalent condition, if we have a unique representation of this thing and every element of H1 is and H2 are commute, so this means we can say that is a internal direct products. So now we have to start today lecture with this theorem. Let G be the internal direct product of a subgroups H and K. So we have a clearly H and is a subgroup of a G and K is also subgroup of a G, and G be a internal direct product of this, then G is means G is if G is internal direct product of a subgroups of H and K, this means H is a normal in G, then there is a unique representation of a G is equal to HK, and H and K are commute with each other. Then he can say that this G is isomorphic to H cross K. So let's begin with the proof. We have to show that G is isomorphic to HK, means we have to define a one map from G to H cross K, and we have to show that the map is defined as a bijective map, bijective homomorphism, and also is we have to share that this whatever map we have to define, it should be the well defined. So first we have to take a GBA an internal direct product. So we take any element of a G can be representation, unique representation of a G is equal to HK, where H is the element of H and K is the element of a K. Now we define a map phi from G to HK in this form. Phi G is equal to in the form of a H comma K, because the elements of a this is are the elements of a Cartesian product of H and K, and this means if G phi of G is nothing but is equal to is the element of a HK. So first objective is this means show that this phi is a well defined. So this means we take a some two elements and G1 and G2 are the element of a G, and because G is internal direct product, so G1 can be written as a sum H1 and K1, and G2 can be written as a sum H2 and K2, and because we have to taking is equal to G1 is equal to G2, we have to objective is G1 is equal to G2, and then we have to show that this is the same as a phi of G1 is equal to phi of G2. So if we have to success to prove this condition, then we can say that this map phi from HK is well defined map. So let's begin. Just take a first we show that this, then we must show that H and K are uniquely determined by this G. So G1 is equal to G2, and which is implies that G can be written as a HK, and G2 can be written in the form of a H. So I just say that G is written in the form of a we have a HK, and then we have to say that G1 is written in the form of a H1 and K1. And because G1 is equal to G2, so this means we can say that simply we have a HK is the same as a H1 K1, where H is the element of H, H1 is the element of H, K is the element of a K, K1 is also the element of H. Now because H1 the element of H and H is a subgroup, so this is also H inverse exists, so we have H inverse HK is equal to we have a H inverse, we have a H1 and K1, and this is nothing but is equal to, you can say this is identity. So this can be written as a K can be written in the form of a H1 in H inverse H1. So H inverse we have a H1, and now K1, and this can be written as a form of K, and you have a K1 inverse is equal to H1 H inverse, now H1, and now we have K1 and K1 inverse, and because K1 is the element of a K, and K is also is a subgroup, so we can say in this form. So we can getting in the form of this. This is nothing H inverse H1 is the same as a K into K inverse, but because you know that this is the element of a H, this is the element of a K. So then these are the same. This means this complete the element of a this is the element of a H intersection K, and you know that at intersection K is equal to identity, because G is a internal direct product. So if this is identity, means we can say that simply is equal to H inverse H is equal to identity, and we also say that K into K inverse is equal to identity. And now if this is identity, this can the H1 is equal to, you have a H, and from here is also we have a K1 is equal to K. So what we getting, this means H1 is equal to H, K1 is equal to K, and then we have a H1 is equal to H, K1 is equal to K. So this means phi of G is nothing but is equal to phi of G1, because you have all the elements of phi of G is nothing but is equal to H1 H and K, and then phi of G2 is nothing but is equal to form of a H1 and K1, and these are the two. So same, this is equal to same. So this means G1 is equal to G2, and then we can say that clearly this map we have to define is clearly this is a well defined map. So first we have to just say that is a clearly is a well defined map. Now we have to try to show that is ontoness. For onto we take a H and K are the element of a H cross K, and as a mesh is in the G, and G is written in the form of a HK is the element of a HK, and HK is nothing but is equal to is the G. And now if you take HK is the element of a H, means H is the element of a H, K is the element of a K, and then HK is the element of a HK. So this means we can say that this is clearly we can say that. So now we have to just say that is onto, and then next we try to show that this phi is 1 1 mapping. So phi 1 1 phi G is equal to phi G1, and then we have H1 K1 is equal to H2 K2, and then if H1 K1 is equal to H1 is equal to H2, K1 is equal to K2, and now if we have H1 is equal to H2, K1 is equal to K2, and these are H1 K1 is equal to H2 K2, and then we can say that H1 H1 K1 is equal to H2 K2, and then we have to just say that because G is equal to, you have a HK, and then this is nothing but equal to, this is equal to G1 is the same as a G2. So this is nothing but is equal to, can we say that G1 is equal to G2, because you have a G1 is equal to nothing but H1 K1, and G2 is equal to nothing but H2 K2, where H1 is the element of H, K1 is the element of a K, H2 is the element of H, and K2 also the element of a K. So this means we can say that simply is equal to G1 is equal to G2. So this is clearly we have a 1 1 also hold. Now next we have to show that this is a homomorphism. So if it is homomorphism, phi is preserve the group operation. Let G1 is equal to H1 and K1, G2 is equal to H2 K2. So we have to just take a phi of G1, phi of G1 G2 can be written as a phi of H1 K1, and then you have a H2 and K2, and now you just see, because you have a H1 is the element of K1 is equal to the element of a K. So using the normality of this, so now this can be written as a H1 and K1 K1 H2 and K2, and then you have a K1 K2, because this every element of a is we have a giving is a group is a direct internal direct product. If it is internal direct product, then every element of H and K are commutes. So H1 H2 K2, and then we have to using this form. Now again associativity H1 H2 K1 K2, and now this means H1 H2 K1 K2 can be written as a H1 K1 H2 K2, and now product of this form, and now this is nothing but is equal to phi of G1, and this is your phi of G2. So by using the here we have to here we using the our group G is a direct product of subgroups S1 H1 H and K, and then if H subgroup direct product of internal direct product of H and K, that unique representation, and every element of H and K are commute. So this means commutative, we can just say that. So this means we have to show that H this phi map we define this phi from G to H cross K. This clearly we have to just show that this two map is defined in this form. So this is we have to take a G is mapped to some H and K types. So this means we have to just say that this means satisfy this phi is our well defined map, and also 1 1 on 2 and preserve the group operations. So this means if phi is by the definition is isomorphism, and if phi is isomorphism, then these two groups G and H cross K are isomorphic to each other. So this completes the proof of this theorem. We can say that if we have a H and K are any two subgroups, and then G is isomorphic to the internal direct products of H and K. So this can be this result can be generalized. We have to taking a two subgroups. We can take a finite number of a subgroup. If it is a finite number of a subgroup, the internal product of this G is isomorphic to the internal direct product of all the finite numbers of a subgroup. So we can extend this theorem into the case of we have a if we have a finite number of a subgroups there. So Hi is a finite number of a G is the internal direct product of a subgroups of Hi, where I running 1 to n, and then G is isomorphic to direct product of a I running for all H of I for each I running 1 to n. So this can be extend into the this previous theorem for a finite number of a subgroup. Okay, let's say we have to discuss this example. This G is equal to you have a Z30 and H1 is equal to generated by 15, H2 is generated by 10 and H3 generated. So I just say that H1 is generated by 15, one means you have a 0 and 15 are the elements of it there. Now if you have H2 is generated by you have a 10, you have a 0, 10, 20, and then you have a if generated by 6, H3 generated by 6. So you have a 0, 6, 18, you have a generated by 6, 6, 12, 30, 24, and then nothing is there. This is it. These are the, and now clearly the order of H1 is equal to you have a 2, order of H2 is equal to you have a 3, and order of H3 is equal to you have a 5. And now because G is abelian, so this means H1 is clearly, this means we can say that this H1 is a normal subgroup of a G, H2 is also normal subgroup of a G, and H3 is also is a normal subgroup of a G. So we just say that we can say that this means this Z30 is isomorphic to H1 cross H2 cross H3. So we just take now just take I just take a, if you take intersection of H1 and H2, if you see this, there is a only common element is equal to 0 identity, and if you take a this means if you take a sum of these two H plus H1 plus H2, so H1 plus H2 you have a different types. So if we just okay, so this means H1 intersection H2 is equal to also identity. Now we just say that order of H1 plus H2 is equal to, so if you feel this, I just say that H1 is equal to you have a 0 and 15, and then you have a H2 is equal to you have a 0, 10 and 20, and now if you take a sum of these H1 plus H2, and then the element of is equal to 0, and then you have a 10, and then you have a 15, then you have a 20, then you have a 5, 10 plus 5 is equal to 25, and 20, 35 is equal to you have a 5, so is equal to 5. Now you see clearly there this is group is nothing but is equal to generated by 5. And now the element of this is equal to order of this H1 plus H2 if you take, and then you have a clearly is equal to 6. So now we have a clearly, if you say see there is a sum H1 and H2, order of H1 H2 is nothing but is equal to 6. And now by the formula also we have a, because intersection of this is equal to identity, so in, size of a order of this is equal to 1. So we can say H1 plus H2 order of this is equal to H1 and H2 upon order of intersection H1 and H2, and is equal to 1. So this means 2 into 3 is equal to 6, and clearly this 6. And now we see this is clearly, you see here H1 plus H2 is clearly generated by 5. So H1 H2 is nothing but is equal to is a then all the elements of this you can just see this is clearly we can say that. So H1 and H2 is sum of this H1 plus H2 is generated by 5. Now we take H1 plus H2 plus H3, and now see this you have H1 plus H2 is this, and then you take an intersection of H3. H3 is generated by 6, so you know that H3 is the form of a 0, 6, 18, 24. And now if you take intersection of a this and this, you have a clearly again you have a identity. So now if you take a sum of these, you have a H1 plus H2, and then we take a plus of a H3. Now you have to take a sum, and then we have to calculating this form. So we can just say that if you find order, and order is nothing but is equal to order of this plus this is equal to, you can say that order of H1 plus H2 into order of H3. H1 plus H2 is equal to 6, and you have a order of H3 is equal to, you have a 5. So is equal to 30. So this means order of H1 plus H2 plus H3 is equal to 30. And now if you take a sum of these three is nothing but is equal to you getting is equal to H1 plus H2 plus H3 is equal to G. So G is the internal direct product of H1, H2, H3, and if G is internal direct product of H1 and H2, H3, then previous theorem said that this G is isomorphic to the group of this. So this group generated by 15, this is group generated by 10, and this is group by 6. So this means Z3 is isomorphic is equal to this is isomorphic to generated by 15, 10, and 6. Okay, now we have to try to one more example. Let G be a cyclic group of order this 6. And now you can just see this, we have a this contains two normal subgroups. H1 is generated by A3, then is nothing equal to E, and H generated by A square, then A square is equal to you E, A square, and A4. And now you see, if you have just take a intersection is clearly is a identity. Now we take a, because this is group is under multiplication, so this clearly this intersection is equal to identity. So now we one more, and now we have to just question is this, as consider Z2 cross Z2, and it is a 4 element. How the 4 elements are this type? Is we have know that Z2 cross Z2 is the element of a 0, 0, 0, 1, 1, 0, and 1, 1. So there is a total is a 4 element into a Z4, and now because of this we can say that either this Z2 cross Z2, Z4 is also is a 4 element, and U8 I take in the form of a 1, 3, 5, 7, and then U8 is also the order 4. So this means Z2 cross Z2 is isomorphic to Z4 or Z8. So it is isomorphic to either Z4 or Z. Now we see because say clearly this is every is not a you can just say that order of, if you find the order of this is clearly 0 into 1 is equal to, you have a 0, 0. So order of this is equal to 2, order of this is equal to 2, order of this is equal to 2. So this means there is a does not exist any element whose order is equal to 4, and but in the Z4 you can just see the Z4, and then you can take Z, because this is Z2 cross Z2 is also not a cyclic, and then element of a Z4 is equal to 0, 1, 2, and 3. If you take a there is a element of this we have to take a 1, and this order of a 1 you just take a, you have a 1 plus 1 is equal to, you have a under addition 4 you have a 2, and then you have a 1 plus 1, and then you are getting 3, then 1 plus 1 is equal to 4, and then you can say that if you have to sorry, 1 plus 1 is equal to 4 is equal to 0, and then there is one element of order 4, and this is a cyclic generated by 1. So this means that 4 is generated by 1, and this means there does not exist any element. This group is a non-cyclic. So that is clearly this Z2 cross Z2 is not a isomorphic to this Z4. Now we to see this element of this. Now you have to take a 3 square is equal to 1. Now you have to take a 5 square is equal to 1. Now you take a 7 square is also is equal to 1. Now every element of this also is a order 2, non-identity element of this order 4. This is a group of order 4, both are the order non-cyclic groups, and then we can say that this is also elements are order 2, here is also the elements are order 2. So, this means Z2 cross Z2 is clearly Z2 cross Z2 is isomorphic to U8, not Z4. So, this means we can clearly say that between these two we have to find Z2 cross Z2 is isomorphic to which one. Okay, so this means we take any element of this, we have a 2b is equal to 0, there is a no element have a order 4, so the group must be isomorphic to U8, not Z4, because in this set this every element is a order 2 in this case. So, this satisfies this condition. Okay, now because we have these two theorems, last is said that the internal direct product of H and K is isomorphic to the external direct product H cross K. For this reason we often do not distinction between the external and internal direct product, and that's why we simply say that is a direct product, because we have to prove that the internal direct product is isomorphic. G is the internal direct product is isomorphic to H cross K external direct product. So, this means these two are will behave like a same, because these two are isomorphic to each other. So, this means we can say that simply there is a we simply call is a direct products of this thing. Okay, now we have to move to the last topic of this series of lectures, and that topic is a structure theorem of finite abelian groups. So, what is a structure theorems mean? In cyclic groups we already see that every group of prime order is isomorphic to ZP, where P is a prime, and we also determine one theorem. We say that if Mn are relatively prime, the Zm is isomorphic to Zm cross Zn, where GCD of Mn is equal to 1 year, they are relatively prime. So, by these two theorems we can say that the isomorphism is there. So, that means we can simply define in this form an abelian group is finitely generated if it can be generated by a finite number of elements. Okay, so now the fundamental theorem of finite abelian groups allow us to express any such group as a product of a cyclic groups whose orders are prime powers, and this theorem implies that any finite abelian group can be represented up to isomorphism in the form of Zp to the power eta 1 plus Zp2 eta 2 power E2, and then prime powers are there, where Pi are the primes, not necessarily all are distinct, and eta is the positive powers is there. The fundamental theorem is say that we can find how many groups are isomorphic up to this form. To appreciate the significance of this theorem, it is tell us that any finite abelian group regard of order can be expressed as a direct product of a cyclic group with a specific order. So, consider for example, we have to consider a group of order 144. In general, there is a one abelian group of p to the power eta for each partition of a eta, that is each wave writing eta as a sum of a positive integer, not that these integer become as the exponent powers of a p. Like this 44 can be, we have factorized into the form of a 2 to the power 4 into 3 to the power 2. There are 5 way to partition into this is 2 to the power 4, 4 can be partitioned into 4, and then 4 can be written in the 3 plus 2, 4 can be written as a 2 plus 2, then can be written in the form of a 2 plus 2, 1 plus 1, and also this can be written in the form of a this all are for 2 cross 2 cross 2 cross 2, and then for 3 to the power 2 can be representing the 2 way 2 and 1 plus 1 and nil do. So, that means we have a total is this, you have to just check is in form we have a representation is a 1 2 3 4 5 6 7, and then we have a total this one again. So, there are total 10 groups we can total 10 groups we can write in this form. Just see according to the our result. That first is we can say that z2 to the power 4 into z2 to the power 3. Now this 2 to the power 4 can be factorized into the form of a 2 to the power 2 into 2 to the power 2. So this or just with a 3 square can be factorized into the 3 into 3, and then second representation is a z2 to the power 4 into z2, and now we can using is this one, this can be representing as a 2 to the power 3 into 2, again 4, and then 3 square, and then again we have a 2 to the power 3 into 2 into z3 into z3, and now we have 2 to the power 3 into this, and then this can be next representation is a z3 by z3, and again we have to take a z to the power 2, z to the power 2, z3 to the power 3, and then this is another representation in this form, and now this is the same thing, and then now this can be written as a z3 cross z3, and this is the sixth way representation we have to write in this form. Now again we have to taking the this is equal to this can be partitioned into z2 into z2. So this we have a z2 square, z2 cross z2, and 3 square. Now 3 partitioned into the form of a this form, and now we have to partitioned this also, and this can be written in the form of a z2 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 3 square, and now we have to partitioned is last time is equal to this form. So that means we can this 144 is equal to 2 to the power 4, and 3 square can be representing a 3 different possibilities of a 10 groups are there in the form of this form. So this means we can write all the elements of this group into this form. For example, another we take a suppose finite abelian groups of order 550, then this can be factorized into this form. Then now we have a for 2 to the power 2 is a 2 representation 2 1 plus 1, and this is 2 to the power 3 to the power 3 is there is a 3 representation 3, you have a 2 plus 1, and then you have 1 plus 1 plus 1, and there is only single representation are there. So that means we can say we have a all these things equal to you have a together this you have to take a one is a z2 cross z2 and z3 z3 z5, then we have to again z2 cross z2 z2 and z3 and z3 square is equal to z9 z5, and now we have to write is equal to z2 cross z2 z27 power 3 and 5, and now we have to take in this way 4 z3 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 z5. Now we have a z4 z3 z9 and z5, and now we have a z4 z27 and z5, and then we have a these are the total 6 representation of this. If you see this is equal to 2 1 plus 1, and this is equal to 3 2 plus 1 and 1 plus 1 plus 1, and then you have a 3 plus 2 5, and there is equal to only single representation of the 5. The total 6 representation for a finite abelian group is this means this z5 z of 540 is isomorphic to any one of this group of 6. And similarly for this second one, first one we have a this is a z144 in this form. So this means this is isomorphic exactly one of the following, and then this way we can say that clearly we have to identify the this factorize, and then this can be written in the form of this thing. Okay, so now so I think this we have to by this theorem we can say into this form we can representing all this groups into this forms there. So I think I have to stop today's lectures here, and we have to continue the how to this finite abelian groups into the last section. If we have to just try to prove some more results related to the finitely structure of a finite abelian group. So thank you very much for this lecture. We continue in the next class for this topic continue. Thank you very much.